I think we are good to go then. So hello everyone, and welcome to the session of Crypto 2020, which is going to be about zero knowledge proofs. Mostly, we're going to have 7 talks. Most of them are going to be about zero knowledge proofs, but I think all of them are going to be about proofs. So that's probably unifying all of them. I'm going to now introduce the authors of the first paper. The paper is going to be called Compressed Sigma Protocol Theory and Practical Application to Plug and Play Secure Algorithmics by Thomas Athema and Ronald Kramer. And I believe Thomas is going to give the talk. Here we go. Oh, Ronald is giving the talk.
You hear me?
Yes.
Okay. Just a second. Okay, good, great. Hello, everyone. So this is about compressed sigma protocol theory and this joint work with my student, Thomas Athema. All right. Okay, so sigma protocol theory, the theory around 3-move zero knowledge protocols is a well-established basis for zero knowledge proofs already for decades. And if we zoom in on the question of how to base circuit zero knowledge on sigma protocols, there are lots of examples of how to achieve sort of linear communication complexity, meaning circuit size times security parameter, basically. Now, in 2016 and 2018, bulletproofs have been introduced by Bootle et al., DuraCrypt 2016, and Bunz et al. At Crypto 2018, where they dramatically reduced the communication. It's no longer linear, but logarithmic. Now, at the core of this method is an ingenious recursive proof of knowledge for quadratic relations on a long secret committed vector in a compact commitment. And this work has at places been presented as a drop-in replacement for sigma protocols due to this dramatic reduction in communication. Now, in this work that I'm now presenting to you, what we'll be discussing is how to reconcile bulletproofs with sigma protocol theory. And the conclusion that we propose is that rather than being a replacement, bulletproofs actually presents a strengthening of sigma protocol theory. So it's a completely diametric position. Now, how are we going to do this? Now, what we're going to introduce is a novel natural circuit zero knowledge protocol from sigma protocols with linear communication. And then using an adaptation of the core bulletproof proof of knowledge, we're going to compress this in a black box fashion as an afterthought. And as a result, we're going to get logarithmic communication or even constant. Okay, so what is our high level approach? So at the highest level, what we're going to do is we're going to deal with linear instances first, so linear circuits only, so to speak, and then linearize the non-linear instances. And from a mathematical perspective, this is perfectly natural problem-solving strategy. The point here is that bulletproof's pivotal proof of knowledge is for a quadratic relation on compactly committed long vector, and that necessitated some reinvention of protocol theory to an extent. So we're going to play this game in a completely different way. So let me first explain how to approach the linear instances. So using appropriate compact commitments to long secret vectors, there is a natural honest verifier zero knowledge sigma protocol for opening arbitrarily linear forms on the secret vector. Yeah. So you can see this in the paper. I'm not going to try to explain this to you now, but it is very natural. And this will have linear communication. Now, the observation that we make here is that we make a suitable adaptation of the pivotal bulletproof proof of knowledge, this recursive proof of knowledge for quadratic relation on a committed long vector that I spoke about in the previous slide. Then what we can do is we can use this adaptation to compress the sigma protocol. Essentially, it's third and final round, which has linear size. The rest is smaller, but we can compress that in a black box fashion. So the result, the overall result, is logarithmic communication. And we've only used the core, an adaptation of the core of bulletproof to just black box compress this last message to get logarithmic complexity. Now, how do we handle the nonlinear instances? Now, what we use is an adaptation of a paper from 2012, ICITS, by Damgaard, Pastro, and myself. This paper ports techniques from information theoretic multi-party computation to, of course, two-party sigma protocol theory. And this is inspired by a combination of my paper with Damgaard and Maurer from Eurocrypt 2000 on MPC from linear secret sharing, and the MPC in the head paper by Ishai, Kushilevich, Ostrovsky, and Sahai. So what does our paper do from 2012? Using one-dimensional homomorphic commitments, one-dimensional meaning single field elements are committed to, not longer vectors. And in addition, with arithmetic secret sharing, we get an efficient sigma protocol to prove long vectors of committed multiplication triples correct. Yeah? All right. So what the verifier does in this protocol, that he does randomly tests local multiplicative properties of packed secret sharings. That's a thing to remember. Now, the observation that we make here is that given compact commitment to, well, the multiplication triples themselves, plus appropriate correlated randomness, we can get a similar sigma protocol, but with a constant number of black box calls to the protocol that I discussed in point 1. Yeah, so that is the compressed sigma protocol for linear openings. As a result, we get a logarithmic size or constant size proof for long vectors of compactly committed multiplication triples. So that's a long way towards zero knowledge. So for the specialized reduction from circuit zero knowledge to this primitive of verifying multiplication triples, what we do is we compactly commit, we have the prover compactly commit to the inputs of a circuit, the outputs of the multiplication gates, and correlated randomness. And now we do a reduction that combines point 1 with point 2a. Now, the inputs to multiplications in the circuit are linear forms on all ancestor variables. So that means that the relevant secret sharings are accessible as linear forms. So then it's easy to see that the rest of the argument boils down to verifying long vectors of multiplication triples. So what we do in addition, so that covers the zero knowledge, the circuit zero knowledge, but we also need auxiliary protocols for what we call compactification. So far, the prover is committed to an input vector that he wants to prove something about, and the outputs of the multiplication gates, and he's committed in the same commitment to correlated randomness. But the reality in practice would more likely be that at the start of a protocol, the prover is just committed to some secret input vector that he wants to prove some property about. So that could be that either he's compactly committed to this vector, or this commitment is dispersed across several lower dimensional commitments, for instance. So if we use the machinery that I just discussed, plus additional ideas, we can compactify this all into a commitment that's suitable for the zero knowledge protocol that I discussed under 2. And the communication will be the same, actually. So this is another modular add-on of our work that is not so explicitly modularly discussed in previous work. Now, when it comes to which platforms would support this type of protocol that I've just discussed. Now, for logarithmic communication, we can base it on the discrete log, same as bullet proofs, strong RSA in class groups. On RSA, if we assume a multi-party setup of the modulus. We have to note that for the discrete log case, which is what that bullet proofs looks at, that our communication complexity is the same, even down to the constants in the big O. The constants is equal to 2. Now, interestingly, there are separate lines of works on zero knowledge snarks that get constant communication instead of logarithmic. And our paradigm also supports that by sticking in a knowledge of exponent assumption, and we get constant communication. As for lattices, it should also work based on lattices, but more work is needed to establish the efficiency, because with lattices you have all the issues about soundless slack, so more study is required. Now, recent work is work with my student Atema and with Sarah Sphere. We have used this theory plus additional ideas to give proofs of K, N partial knowledge with logarithmic complexity. And there's recent or an upcoming work by Schoenmakers and Segers using the compressed sigma protocols for verifiable MPC. So I don't know how much time I have left.
It's about 1 minute, so
Okay.
including the time that we wanted for questions.
Oh, okay. Well, so then let me just finish with some historical remark. This idea of getting very fast zero knowledge out of compactly committed long vectors that allow fast opening of linear forms goes back to 2010. In fact, the paper is from 2012. But when we started talking about it, which was actually at the PhD dinner of Nacho Cascudo, we worked that out much later. It became clear that we could do that result we had in the paper much nicer if we had compact commitments where we could open linear forms very efficiently. So it took, I asked around for several years, nothing was known. But then the work of 2016, 2018 came along, and finally we did it. Now I know why it had to wait for so long, because it waited, this work waited to be done by Thomas and me, and Thomas started a few years back. So I think that's a very good reason. Thank you very much.
Thanks, Ronald. We can have one very quick question while the next speaker puts the screen on, which you can see in the chat. Question says, how does this relate to linear IOP and linear PCP abstractions? Can one view your techniques as a method of compiling linear IOPs and PCPs into logarithmic or constant size cryptographic arguments?
We discuss a lot of related work in the paper as with respect to linear PCPs. I remember having had some discussions on how related this work is to that part, but I think I came to the conclusion, at least preliminary conclusion, that this is very much tied in with techniques around complexity theoretic assumptions, and it uses some tricks that cannot so easily be abstracted away from the complexity theory. And most of the work on the linear PCP appears to me a complete transitioning from information theoretic methods to complexity theoretic methods. Part of our work is of that kind as well, but especially at the part of the this recursive proof of knowledge, that seems so very much tied with the complexity theory. So I don't know, that's an interesting question.
Thank you, everyone. So I think we have no more questions, and we can go to the next talk. So I think, Ronald, if you unshare your screen, the next speaker can share it. Thank you so much for the talk. So the next talk is going. The next talk is going to be on tight parallel repetition theorems for partially simulatable arguments by Itai Berman, Iftar Hartner, and Eliad Sfadia. And Eliad is giving the talk.
Thank you. Do you hear me?
Yes.
Okay, thank you. So I'm Eliad Sfadia, and I'm going to briefly describe our work, tight parallel repetition theorem for partially simulatable arguments. I'm going to work with Itai Berman and Iftar Hartner. So basically, this work is about hardness simplification. That in general, it's one of the most fundamental topics in computation. In general, it means, can we turn a weakly hard primitive, let's say a weakly secure algorithm or a protocol, into a very hard one or secure one? Usually, we want to do it while preserving the other desired properties of the original primitive, like efficiency. And the focus of this work is the amplification of interactive arguments, also known as computationally sound proofs, where these are proofs where the soundness guarantee only holds against computationally bounded provers. And as you all know, this is an important primitive in the cryptography. So in the amplification of iterative arguments, the main goal is to find a generic transformation to reduce the soundness error of any argument. So let's say we have some argument PV, where P is the prover and V is the verifier, and the soundness error is 1 minus epsilon. It means almost no soundness guarantee. A cheating prover can win with probability almost 1. And then we want to apply this generic transformation and to turn it into a similar argument, which has soundness error negligible. Okay, So the most natural way of doing such a generic amplification is by repetition, because hopefully if we repeat the execution many times, then it will be much harder for the prover to win in all the executions. And so the first option is do a sequential repetition, just repeat the execution many times sequentially, one after the other, with independent coins, and the verifier accepts if all the sub-verifiers in all the executions do. This, in almost all settings, reduces the soundness error. If we start with y minus epsilon, it reduces to y minus epsilon to the n, to the power of n. But the problem is that it blows up the round complexity. So an alternative way of doing repetition is by parallel repetition, where in each round, each party sends n messages that corresponds to the n executions. And by that, we preserve the round complexity, which is great, but does it improve the security? So for specific type of arguments, we know that it does, like public coin arguments, but in general, the answer is no. And there are concrete examples of arguments that, let's say, have soundness error half. You repeat them a million times in parallel, and the soundness error remain half. So, but it turns out that there is a way to somewhat overcome this problem using a random termination. So let's say we have some arbitrary argument PV, which has M round, and now let's slightly change the verifier such that in each interaction round, it flips a coin, which is 1 with probability 1 over M. If the coin is 1, it just accepts and aborts. Otherwise, it acts like the original V, continue to the next round, and then it flips a coin again and again in the end. And if none of the coins were 1, then it just acts like V and accepts if V does. So it seems like a very stupid thing to do, because now the prover has a better chance to win. But it turns out that no matter what protocol you started for PV, if you look at the random terminating variant of it and repeat it n times in parallel, then the soundness error must reduce in exponential rate in the number of repetition n, which is great. The only problem is that this is still far, the hardness result is still far by a factor of m to the 4 over epsilon in the exponent from an ideal decreasing rate of 1 minus epsilon to the n. So after this work, it's still left open whether there is a better generic method to amplify arbitrary arguments, or maybe this method achieves a better, a stronger decreasing rate, but just the analysis is not tight. So it turns out that this is our result. The analysis is indeed not tight. And the soundness error, if you take an arbitrary argument and you repeat it, you look at the random terminating variant of it, repeat it n times in parallel, then the soundness error reduces by a much stronger decreasing rate of n over m, which is only far by 1 over m from optimal decreasing rate of n. So this is a significant improvement over a hardness result, and this immediately yields tighter bounds for many specific amplifications. And also, this is generalized to partially simulatable arguments, which is an extension of random terminating arguments. And a few words about the proof. This is basically achieved by bounding a relaxed variant of the KL divergence between the distribution that induced by the reduction and its ideal variant, rather than bounding the statistical distance like previous work did, which is inherently non-tight. And our second result is a matching lower bound. We showed that for every m and epsilon, there exists an argument PV, such that if you look at the random terminating variant of it and repeat it n times in parallel, then there exists an attacker that can win all the n random terminating verifiers with probability 1 minus epsilon to the n over m, which means that we cannot hope that the random termination will give us something better than this decreasing rate. This 1 over f factor is really essential. And that's it. Thank you.
Thank you so much, Elliot. If there is any questions, please let us know in the chat on Zulia or in the chat panel here. We have about 3 minutes for questions. We can go faster to the next talk. If there is no question, I have one myself, which might be very easy. So maybe I go ahead and ask it. So does the reduction in the proof need to be non-uniform, or it handles everything uniformly? So you need to assume non-uniform soundness
also
against
for non-uniform. It was also for non-uniform and for uniform. It's not
uniform is a stronger,
yes,
sure. So
yes.
sometimes you need to kind of the reduction
Yes,
is
no,
sometimes
but,
non-uniform.
Yes.
The reduction is uniform. Got it. And it's the second one is not a very kind of well-formed question. Do we have a reason that the KL divergence can't be used? It's not a well-defined question. I understand. It's a research question. It's not an assumption. It's a tool. But
why we use the relaxed variant?
Yeah.
And not KL? So the problem is that in this reduction, so the KL, you can bound the KL diversion like in the public coin case, but in the random terminating and the partial simulatable case, the KL diversion might be infinite. And somehow it's infinite because of some small events that makes it infinite. And in our analysis, we came up with a relaxed variant that somehow eliminate these small events but still use the good properties of the KL diversion. So this is basically the.
Appreciate it. So thanks again, the speaker of this talk, Eliad, and we can go to the next talk of the session if there is no more questions. But there is one. Are there any reasons to use sequential repetition, or is this just objectively better? You mean as a?
So I mean, what I mean, the sequential repetition in almost all settings decreases by an optimal rate, but you pay the number of interaction rounds is n times more. If you want to, if it's okay with you, then you can use a sequential repetition. But usually we want parallel repetition in order to save this interaction route, which can be very expensive.
Yes. Thank you. Okay. So we're gonna move to the next talk, which is going to be about. I think if you unshare your screen, Eliad, thank you so much.
Okay, sorry.
So now the next talk is going to be about interactive proofs for social graphs. And I hope one of the speakers, one of the authors who is going to present that paper would share their screen. Is it Elon or? So that let me introduce the authors, Liran Katzir, Clara Shikerman, and Elon Yogev. And if any of them are here, they should go ahead and share their screen. So my guess is that maybe they're not. So in case,
I don't find
in case we have the presenter for the next paper, which is the measure and reprogram technique, if they are here, they can go ahead and present, and then we can check with the presenter of the paper that we couldn't reach out to later on during the session.
Yeah, sure, I can go.
Yes. Okay, so I guess I have to hand it to Fang, who is going to introduce you and the rest of the session. In case we hear about the other paper, we will get back to them. But Fang, go ahead, please
okay.
Go ahead. And,
all right, I'll take over. Okay, our next talk will be the measure and reprogram technique 2.0, multi-run, Fiat-Shamir, and more. We're going to hear proofs and also something about quantum. So this is from Yella Dunn, Serge Fer, Christian Mayer, and Yella will be giving the talk. So Yella, the floor is yours.
Yes, thanks. Thank you for the introduction. Our work is about proving Fiat-Shamir digital signatures, and in general, Fiat-Shamir zero-knowledge proof systems secure against quantum attackers. Where by secure, we mean securing the quantum random oracle model. We extend the existing theorem technique by Dunn, Veer, Mayens, and Schaffner to a larger class of applications, notably multi-round Fiat-Shamir signatures, bullet proofs, and sequential OR proofs. And finally, we also show that the security reductions that we get from applying this technique are tight. While our result concerns a general QROM technique, I'll start by explaining the main motivating example, which is the multi-round Fiat-Shamir transform. There exists something called a 2n+1 round public coin interactive proof system with constant or logarithmic number of rounds, where some prover can prove its knowledge of a secret key to a verifier by sending a sequence of messages, the so-called commitments, to which the verifier replies with a uniformly random challenge, and the prover sends the next commitment, etc., until it reaches its final response. But if we want to apply this protocol in a signature scheme, we need it to be non-interactive, meaning that we want the prover to send all of these messages in one go. However, since it will now no longer receive these random challenges from the verifier, it will have to compute them himself. And it does so by taking the hash of each of these commitments, using some public hash function h. Public so that also the verifier has access to it and can recompute the challenges, and then check some verification predicate on these commitments, the response, and the challenges produced by h. Now, to prove security, or more precisely to show that this non-interactive scheme is as secure as the interactive one, we turn to the quantum random oracle model, where we model this public hash function h as an external random oracle, to which all parties have quantum query access, which means that the function cannot be computed locally. So any adversary in this protocol will have to make queries to the external oracle, but they can consist of a quantum superposition of inputs. So if the adversary makes a query, what it actually does is it sends over a quantum state to the oracle. Now, in many also classical random oracle model proofs, what we want to do is show the existence of some simulator S that can simulate the oracle to A and also observe the queries that it makes. But as you might be aware, observing a quantum state may cause it to collapse, which in turn can influence the behavior of the adversary, so that in general, we can no longer predict what the adversary is going to output, which is a shame because the simulator might need this output in the security reduction. But then comes our result on the multi-input reprogrammability of the QROM, which says that if we have such a scenario where some adversary makes Q quantum queries to a random oracle H, before outputting an array consisting of n different hash inputs X, as well as some additional output C, such that on some arbitrary predicate V holds of C these X's and the corresponding hash values, then indeed there exists a simulator that can choose n of these queries at random, measure them, and upon the hash inputs found in the measurements, reprogram the oracle to some fresh random values theta. And the adversary will now still produce some output X bar, C bar, of which the same predicate V holds, but now with respect to the fresh random values theta. And we can relate these probabilities for any particular choice of hash inputs X naught up to this loss of order Q to the power 2n. And that is exactly what we need to show that the advantage of the best adversary against the Fiat-Shamir transformed non-interactive scheme is at most order Q to the power 2n times as big as the advantage of the best adversary against the interactive scheme, which is what we needed for security. Thank you.
Okay, great, thanks. And I think we have time for a couple of questions. Are there any questions from the audience? Okay, now I have a question actually. So you're bound this Q to the 2 to the n, is that tight?
Yes. Yeah, we show a Grover-based attack against the 3-round schemes, showing that the Q squared loss is optimal in that case. And this holds for pretty general, typical Sigma protocols. And then we built some somewhat more artificial multi-round schemes by sequentially repeating these Sigma protocols. And then we show an attack against that scheme, which boosts the advantage of the adversary by Q to the power 2n.
Okay.
So
cool.
that so yeah, in general the reduction is tight.
Cool. Thanks.
There are also questions in the chat. First, Yevgeny asks, how big is n in your application? Constant?
Well, yeah, I mean, I guess for practical purposes, it should be constant or logarithmic to not blow up the loss too much. But it works for general n.
And Ran asks, how important is it that h is uniform over the Boolean cube? For example, what if h has some structure?
Well, yeah, our proof only works for uniform h. I'm not entirely sure if there isn't some way to make it work in the other case, but our proof works only for uniform h.
Okay.
Yevgeny asks also, how does it compare to Gendry et al.'s technique for Fiat-Shamir?
Well, the Sandry technique, if you're referring to the 2019 paper, that has a loss of order q to the 9th versus our q to the power 2 in the 3-round case. And I'm not aware of any extension of that technique to multiple rounds.
Thank you.
Okay, excellent. Thanks, Yela, for the excellent talk, and also thanks for all the nice questions. And we can take further questions to the Zulip chat. And okay, we're going to move on to the next one. So our next talk will be Fiat-Shamir for repeated squaring with applications to PPAD hardness and VDFs by Alex Lombardi and Vinod Vakutanathan. And I think Alex is going to give the talk. So Alex, if you
yes,
can
sorry,
share
1
screen.
second. I need to screen share. Sorry.
No problem.
That's okay. Yeah, I want to remind everybody, please type your questions in Zulip, and also, if you like, in Zoom as well. It's a little bit quiet in the Zulip.
Okay, can you see?
Yep.
Okay, sorry about
We
that.
see everything. So we see everything. In case you want us to see the kind of just
Wait, this is correct though, right?
No, it's good.
Yeah.
Yes.
Okay, sorry about that.
Okay. All right, the floor is yours.
Okay, hey everyone, I'm Alex. I'm going to be talking about repeated squaring, Fiat-Shamir for repeated squaring with applications to PPAD hardness and VDFs. In the short talk, I'll explain to you what exactly we prove, and I can refer you to the paper on ePrint or a longer version of this talk on YouTube for more details. So the Fiat-Shamir transform is a heuristic mechanism that we just heard about actually for converting public coin interactive protocols for some task into a corresponding non-interactive protocol for the same task. And I know you all just heard this, but the way it's done is you take an interactive protocol where the verifier's messages are uniformly random, and you replace the interaction with the computation of a hash function. So in the corresponding non-interactive protocol, the prover iteratively computes its messages as it would in the interactive protocol, but computes the verifier messages itself as hashes of the protocol transcript up until that point. So this is at least a candidate way to get a non-interactive protocol. It's been around in cryptography for over 30 years by now. It's quite ubiquitous. What was said originally was that at least heuristically, it appears that the soundness of the protocol is preserved by the transformation. In terms of what we can prove, at least classically, we can show that soundness holds in the random oracle model in very high generality. So for essentially any protocol you would care about, if you model the hash function as a random oracle, then you can show that the Fiat-Shamir protocol is sound. But if you want to argue soundness in the standard model, that is with a concrete hash function that you can compute as opposed to querying as an oracle, then very little was known. It's a big open question in theoretical cryptography to figure out which interactive protocols we can actually instantiate Fiat-Shamir for in the standard model, and what cryptographic assumptions on the hash function you need to make to prove the soundness of the protocol. So up until a few years ago, essentially no positive results were known about this. But recently, we've finally been able to show that at least in some special cases that you can do Fiat-Shamir in the standard model. So let me explain the state of the art as of this paper. So first of all, we're going to assume that the interactive protocol is statistically sound. That is, it's sound against computationally unbounded provers. This is a fairly large restriction, but subject to this restriction, it's known that if you make a strong enough assumption about the hash function, then Fiat-Shamir for any such protocol, at least if you say restrict to constant rounds or not too many rounds, you'll get soundness. Unfortunately, the assumption is incredibly strong, like very non-standard, and you would not want to be caught making such an assumption. But from a theoretical perspective, it's a nice feasibility result. More recently, we were able to show that for a very specific class of interactive proof systems, you can have a Fiat-Shamir compiler under a standard cryptographic assumption. More recently, it's been shown that you can do it under the learning with errors assumption. And then finally, I want to say, because of the relevance to this work, that's for a certain intermediate class of interactive proof systems, not all of them, but more than the smaller class. We know how to do Fiat-Shamir under a strong assumption that is not quite as strong as required for the general purpose results. So I'm pointing this out because the sum check protocol, which is quite important, is in this class. But we don't know how to compile it under, or we did not know how to compile it under a standard cryptographic assumption as of this work. So as you can see from this state of the art, there is no succinct interactive proof system that we could provably instantiate Fiat-Shamir for under a standard assumption. This was an interesting open problem. So in this work, we're going to stare at a particular succinct interactive proof system and do Fiat-Shamir for it under a reasonable assumption. So the computational problem underlying the protocol is the repeated squaring problem. So you have some RSA modulus n and a group element g in Zn star, and you want to iteratively compute, or you want to compute the result of an iterated squaring of g done many times. So you want to compute g to the 2 to the t mod n for some large value of t. It's believed that this problem is hard, namely it should take about time t, even sequentially, and there are important cryptographic objects like time lock puzzles based on such an assumption. So more than this just being an interesting computational problem, there's a nice succinct interactive proof system for this computation. It was introduced by Pietrzak a couple of years ago. Very quickly, the way it essentially works is the prover is repeatedly forced to send some halfway point of the computation it's supposed to be doing. And then the verifier computes a random 2-to-1 self-reduction of 2 subproblems to reduce the entire problem to a statement of size half of the original statement. By doing this recursively many times, you get a succinct interactive proof system for this language. So you can at least heuristically apply Fiat-Shamir to this protocol, and you can get soundness in the random oracle model. What that means, again, is replacing these verifier random challenges with hashes of the problem statement and the prover messages. But our question is whether you can do this in the standard model. And we show that under a reasonable assumption, you can. So here are our results. If the learning with errors problem is sub-exponentially hard for a large sub-exponent, it's not a 2 to the n to the epsilon type assumption, but a 2 to the n to the 1 minus epsilon type assumption, then we can do Fiat-Shamir for this protocol with verification time 2 to the n to the epsilon, so some small sub-exponential verification time. Just for reference, this is way less than the amount of time it takes to decide the language. So this is our main result. We can get smaller verification time by making a stronger LWE assumption. And all of the assumptions we make for all of these results follow from the hardness of some worst case lattice problem. Even the assumption that that gives you native polynomial time verification. So I think of the first result as the main one, and the second and the later two are just getting different quantitative trade-offs. So this is our main result, And we immediately get two cool applications because doing Fiat-Shamir for this particular protocol gives has nice implications. So one thing that we get is hardness in the complexity PPAD, which captures the hardness of computing Nash equilibria in game theory. So we can show that if the repeated squaring problem is sub-exponentially hard and LWE is sub-exponentially hard for this larger sub-exponential, then we get hardness in PPAD. You again get similar results with different trade-offs based on the other two results from the previous slide. We also get standard model verifiable delay functions with sub-exponential evaluation time based on this based on the sub-exponential assumptions, and smaller evaluation time based on the stronger assumptions. This of course requires assuming sequential hardness of repeated squaring so that you get a guaranteed delay. So what I like about these results is that we're making strong but sub-exponential assumptions about well-studied problems, and as a result, we get a succinct non-interactive argument for a non-trivial language that has these cool applications. So just a word on related work. In terms of verifiable delay functions, there wasn't really anything known in the standard model based on standard cryptographic assumptions before. For PPAD hardness, we have a few works. They're not based on standard assumptions, but they're works worth mentioning. So we were able to get PPAD hardness previously based on obfuscation, as well as based on the soundness of Fiat-Shamir for both the sum check protocol and the squaring protocol. But before we did not have an instantiation for the Fiat-Shamir hash function based on a standard assumption. And then finally, concurrently to this work, Kalai-Panath and Yang gave a different construction of a PPAD hard instance based on a falsifiable assumption on bilinear maps that does not go through Fiat-Shamir, and you'll hear about this from Lisa in the next talk. So I, of course, don't really have time to explain much about our techniques, but let me give a clickbaity one-sentence explanation of what we do. We do homomorphic index calculus, meaning that in our security proof, we actually evaluate an index calculus algorithm for discrete logs under a homomorphic encryption scheme. If that sounds ridiculous, it is, but see the paper or the longer talk for more details. And that's all I wanted to say. Thank you.
Okay, thanks, Alex. I think we can take a quick question. Is there any? Okay, maybe let me ask one. So for the PPAD hardness, is there any hope to kind of remove one of the two assumptions? Because right now you have both.
So, I mean, if you're doing Fiat-Shamir for a squaring protocol, then you need to assume that the underlying language is hard to getting a succinct argument for a language is not interesting if the language is itself easy. So there's some follow-up work actually that appeared on ePrint a few weeks ago that manages to instantiate Fiat-Shamir for sum check, and this gets rid of the squaring assumption and also weakens the LWE assumption. So I'm sure the community will be hearing about this more in the future.
Okay, excellent. All right, thanks, Alex. Again, I think we can move on to the next one. So our next talk will be also about PPAD hardness. It's delegation with updatable unambiguous proofs on PPAD hardness by Lisa Yan, Yael, Taman Kalai, and Omar Panath. And I think Lisa will be giving the talk.
Right.
So Lisa, the floor is yours.
Thank you. So, all right, can you all see this? Okay. All right, so yeah, thank you for the introduction. So our work is about delegation schemes and their application to PPAD hardness. So in a delegation scheme, you typically have a weak machine, such as a smartwatch, that wants to learn the outcome of a costly computation. So he asks a more powerful machine, such as the cloud, to perform the computation and to send back a proof. And the verifier will just check the proof in much less time than it would take to perform the original computation. And so the question underlying delegation is, can we actually construct protocols where verifying is faster than computing? So our focus today will be on staying in the standard model and relying on falsifiable assumptions. And so in this model, the only schemes we had for delegating computations up until very recently were what we call privately verifiable, where the verifier needs access to some secret trapdoor information in order to check the proof. And what we'd really like is to have what we call publicly verifiable delegation, where the statement and proof can just be checked by anyone without needing trapdoor information. And the primary motivation for publicly verifiable delegation is they're very essential to decentralized applications such as cryptocurrencies and blockchains, where you really want anyone to be able to verify these public proofs. So the prior works on publicly verifiable delegation up until last year and this year relied on strong assumptions. And last year, the only publicly verifiable delegation scheme we have for general polynomial time computations is our previous work that constructs a scheme based on a bilinear group assumption. And what we do in this work is we build upon this scheme to make its proofs both updatable and unambiguous, both based on this same assumption. So the first notion that we achieve is updatable proofs. And this notion, introduced by Valiant, considers a long computation that's carried out over many separate iterations. And the idea is that as the computation progresses, you have a proof for the computation performed so far. And as someone performs the next block of the computation, he'll update the proof, and this new proof completely replaces the old proof. It proves like all the computation that's been performed up to this point. And what we want in updatable proofs is for this update procedure to be efficient. And what we also want is for the proof to remain succinct. So the proof shouldn't grow with the number of updates. And the idea is that in like decentralized applications, you may have a long computation carried out through many different updates, and you want the proof and verifying the proof to still remain efficient. So previously, we only had updatable proofs based on snarks, which are only based on strong assumptions. And as I said, we get updatable proofs based on a falsifiable bilinear group assumption. So the second property we also get is the notion of unambiguous proofs, which says that any prover cannot produce two different accepting proofs for the same statement, except with negligible probability. And the primary motivation for unambiguous proofs is their application to PPAD hardness. So formally, our result is publicly verifiable delegation with updatable and unambiguous proofs based on this bilinear group assumption, in which the adversary is given a 3 by alpha matrix of group elements for logarithmic alpha. And it's hard to distinguish whether this specific element T is a higher power of S or an independent random element. And this assumption we believe is new, but is similar in spirit to the wide range of bilinear group assumptions made throughout crypto, and it holds in the generic group model. And so we use this delegation scheme to show PPAD hardness following the blueprint of Chanduri et al. And so what we obtain is PPAD hardness just based on the quasi-polynomial hardness of this assumption and any hard language L. So if you're willing to assume non-uniform ETH, then this gives you a hard language L that suffices. So as Alex also mentioned, showing PPAD hardness has been an important problem. And up until recently, we only had it based on strong assumptions or the assumption that Fiat-Shamir is heuristically secure. And only recently did we have PPAD hardness based on the LWE assumption. And you can view these concurrent works as essentially constructing a delegation scheme, but only for a particular language, such as the repeated squaring language. And so in our work, we we kind of went the other way. We constructed a delegation scheme for any language, and then use that to show PPAD hardness. So in summary, our results are a souped up delegation scheme based on a falsifiable assumption, and PPAD hardness also based on this assumption. And I'll just say in a nutshell how we get our results is we actually obtained these updatability and unambiguity properties without relying on strong assumptions by using the power of what we call local proofs in non-deterministic delegation. So essentially, these two properties can be obtained by relying on strong assumptions for non-deterministic delegation, but we can relax that assumption significantly if we essentially use local proofs, which means that we use a single proof to do many separate extractions, and we piece together these extractions by showing that they're consistent. And this is kind of in a nutshell how we get updatability and unambiguity, and also PPAD hardness under our assumption. And the full version of our work will be up soon, but in the meantime, feel free to refer to the proceedings or email us. Thank you.
Okay, thank you, Lisa. And we have time for questions. Let me start with one when people are typing in their questions. So I'm just curious, is there any real world motivation or application for the unambiguous proofs?
Yeah, so this is actually a question we have as well, because the only motivation we had for it was to get PPAD hardness. So we don't know of any applications, but it seems like a very interesting property that you kind of have like this canonical proof. And so we'd be happy to, talk with anyone that wants to discuss it further.
Cool, nice. Are there other questions? Well, I don't see any from the Zoom chat and Zulip either. Well, actually, I'm curious. For people, if I want to pick up, PPAD hardness from crypto assumptions, what would be a good starting point? I was a little bit scared about that slides with all the references.
So I think, yeah, the thing, I mean, Alex and I probably both would have liked to talk a little bit about the reduction from like these delegation schemes to PPAD hardness, because it's very interesting. That follows the blueprints, that transformation is folklore, but probably first written in the Chanduri et al. Paper. I think our proceedings also has a general proof from delegation to PPAD hardness. So I think that's where I would go to understand how crypto can be connected to PPAD.
Okay, excellent. Thank you again, Lisa. If there are no further questions, let's move on to the next one. So our next talk will be New Techniques for Zero Knowledge by Marshall Bell, Dana Dachman-Solid, and Mukul Kulkarni. And I believe Marshall will be giving a talk. Marshall, the floor is yours. Marshall, are you there? We can see your shared slides, but we couldn't hear you.
Sorry. Can you see now?
Yeah.
Can you hear me now?
Excellent.
Sorry about that.
Yeah, please go ahead.
So yeah, I'm excited to tease you with some new techniques to zero knowledge, or rather old techniques, but new to zero knowledge. This is with Dana Dachman-Solid and Mukul Kulkarni. So right, we're interested in this work, we're interested in zero knowledge and witness indistinguishability. I'm not going to go into detail about what these notions are. Hopefully you all are familiar. Otherwise, you can see my talk or other work. But we're particularly interested in zero knowledge protocols and witness indistinguishable protocols where interaction is very limited. So ideally, the prover is just sending a single message to the verifier. We're interested in this setting where you have very limited setup. At most, a uniform random string, and ideally in the plain model with no CRS whatsoever. And we are also interested in such protocols that are very expressive. So they hold for all of NP or even AM. And sort of our perspective in this work is, overarching perspective is to try to trade prover complexity, so increase prover complexity, and by doing so, minimize the assumptions necessary to achieve these notions of zero knowledge and witness indistinguishability. So we consider sort of two settings where the prover is much stronger computationally than the verifier. So one is sort of this traditional setting where you have a polytime verifier, and the prover is running in super polynomial time. And we also consider a new setting that we introduced we call fine-grained zero knowledge or fine-grained witness indistinguishability, where the prover is polytime, but the verifier is actually in a much weaker class. So here, NC1, which is log depths circuits, so very fast parallel computation. What exactly do we mean by fine-grained zero knowledge? Well, in the same way that we understand zero knowledge in the traditional setting, where we should be able to simulate interaction with an adversarial polytime verifier in polynomial time. In the fine-grained setting, we want to simulate the interaction with an adversarial NC1 verifier in NC1. Okay, and so. In this with our perspective, there's sort of some new challenges, new obstacles are introduced. And just very briefly, what happens, so imagine we want to, we have a witness indistinguishable proof system and we want to prove something about composability. We want to switch from witnesses 1 to witnesses 2. We have an adversarial verifier that's interacting with these two provers. So typically what we would do, right, is we would show a hybrid argument. We would first switch the first witness on the left and then switch the witness on the right. And this is shown via reduction, right? The reduction, this efficient reduction is going to run the verifier and the prover on the witness 1. And then we'll use this to break the witness indistinguishability of the proof system on the left here. The problem in the inefficient prover setting, obviously, is this reduction can't actually run the prover. And so for composition, this isn't, or this specific composition at least, this isn't too big of an issue, but we are interested in constructing, we were looking at this construction of ZAPs, which are 2-round witness indistinguishable proofs from NISIX, and this becomes quite a serious problem here. And our solution is a repurposing of an old idea due to Nissan and Wigderson, who are trying to de-randomize based on hard, on average problems, and use this combinatorial designs that they introduce. And I advise you to sort of look at my longer form talk, where it's a pretty cute idea, and we believe it will have other applications. But just to sort of summarize here, what are our results? So in the traditional setting, I'm not going to tell you what all of these acronyms are here, but just to highlight, in the traditional setting, we show ZAPs from one-way permutations with inefficient provers. And prior to this, we only knew ZAPs, these 2-round witness indistinguishable proofs, from trapdoor permutations. So it's from cryptomania style assumptions. So we get it down to minicrypt. And in the fine-grained setting, we show sort of NC1 ZAPs from this worst case hardness assumption that NC1 does not contain log space, or actually sort of a strengthening of this. But yeah, that's it.
Excellent, and thanks, Marshall. As you can see from the Zoom chat, there are exponentially many praises for your nice slides. Maybe the first question would be, how did you make it?
Keynote. I just drew on Keynote, but thank you.
Okay, are there more serious questions? Oh, I saw one from Zulip. So this is from Rahit. Is NC1 more interesting because of prior work on any other intrinsic reason?
Yeah, it's interesting, I guess, because we have a lot of tools there, like this whole Ishai Kushalevitz framework for doing things. That's why we look at it. I think other fine-grained regimes would be very interesting, but yeah, beyond NC1, we don't have a lot of tools, I guess is the issue.
Okay. Are there any other questions? Okay, if not, we can
On to the last talk of the session.
Yeah, I'll hand it over to Mohammed.
So thank you again. So we are going to now have the last talk of the session on interactive proofs for social graphs by Liran Katsir, Clara Shikleman, and Eilon Yogev. And Eilon is going to give the talk. Go ahead, Eilon.
Hi, thank you. Let me just share the screen and minimize. Yeah, okay. So can you guys see it? Yeah, okay.
Yes, everything good.
So thank you. This is joint work with Liran Katsir and Clara Shikleman, interactive proofs for social graphs. So let's start, if it moves, yeah, let's start with social graphs. These are large and influential part of everyday lives of billions of people. We all use them. And it's not that only that they collect data and we use them, they really become like this new and modern approach to study society and human relationship. There are many commercial companies and private companies, Facebook, Twitter, TikTok, others, but you could also think about DBNP or even search engines can be modeled as a social graph and other virtual assets. Something important is the health of a social graph. There's different measures concerning the health of the social graph. These companies publish reports concerning the health of their graphs. Let's focus on one main measure, which is the size of the graph. Okay, the number of nodes, the number of active users. For example, Facebook acquired WhatsApp for this steep price of $16 billion, and it was calculated by a $40 evaluation per user. So the size of the graph was really a big issue. And down here, you can see part of Facebook reports saying that they have 1.73 billion active users, daily active users, and 2.6 billion monthly active users. And these reports might be potentially amendable by financial or political incentives, okay? They have some incentive to report false numbers. And so should we trust these reports? Can we trust what's written inside? And our answer is that it's crucial to have an independent estimate of these measures. And the main challenge is that the graph is huge, okay, but not only that it's huge, that it's a hard computational problem, but the access to this graph is limited, okay? We do not have access to the full Facebook or Twitter network. Instead, what we have access to a public API, okay? We have public access. This usually contains two types of queries. The first is membership queries, where you give an ID. So you give some ID from some very large possible universe of IDs, and then you can verify that this ID exists. And usually you get some user profiles, you get some metadata about this ID, this node. So perhaps the name, the age, and so on. And second, you have a neighborhood query. So again, you give an ID and you get the list of neighbors of this node in the graph. Or if this list is large, possibly you give a ID and I and you get the ith neighbor. So very, very briefly, there's a lot of previous work, but there are previous work that use this public interface, okay, without relying on Facebook or other companies to get an independent estimate of the size of the graph. And for example, Ye et al. And Katsir et al. In previous work, they needed n to the alpha queries. So for some constant alpha that's smaller than 1, so some polynomial in n many queries to estimate the size of the graph. So this is still a lot of queries, and we ask, can we estimate social graphs measures using few queries, so let's say polylog n, while still having no trust in the graphs provider? And the answer to this is to introduce interactive proofs for social graphs. So this is the model. We have a verifier, we have a prover, okay, and standard interactive proof. The instance that we're talking about is the graph. The verifier doesn't have complete access to the graph. So this is very similar to an interactive proof of proximity, okay? He has only Oracle access to the input. But instead of just reading special parts, special bits of the input, the access he has is exactly through these two through these two Oracle queries. So one is membership, okay, I can see if ID exists, and the second is neighbors. And let me already say at this point, these two things are important. It lets us do a random walk in the graph. Okay, so you can take an ID, ask for a neighbors, select a random neighbor, and then visit this neighbor and ask for its neighbors and so on. So you can perform a random walk in the graph. Let me already say some criticism about our model. So we assume here that the graph is fixed. So the Oracle answers to the graph are returned truthfully. And you can ask, why is that? Like if Facebook is returning our answers to this Oracle, you know, they might as well lie there as well. So there's a few answers for that, but first, it's very hard to distinguish honest users from this verifier, okay? Because its queries seems like legitimate queries. And second, it says that if they want to lie in the reports, they must materialize this lie physically into the network, okay? So this forces them to work a lot to lie instead of just modifying a few numbers in a report. So what is our main result? So given a graph G on n vertices and with mixing time tau, okay? So again, mixing time is the number of steps you need to do in the graph until you reach the stationary distribution, and average degree delta, so just the average degree of the graph. We construct a doubly efficient interactive proof in the social graph model, okay? So in the model I just presented, for estimating the size of the graph, okay? Where you give me approximation error epsilon, and we verify that the size that they claim, this n tilde, is at most 1 plus minus epsilon times n. So you just have some small fraction of error, okay? Let's say less than 1% error. It's a two-message protocol. It's a public coin protocol. The number of queries that the verifier performs is only 1 over epsilon squared times tau times delta. So usually in social graphs, and this is why we call it social graphs, the tau is not large. These graphs are well mixed, and delta is not large. And epsilon, you can think of it as some small constant. So this is really polylog n. And the prover running time, so we said it's doubly efficient. The prover running time is also small, so it's quasi-linear in the network size. So this is something really efficient that can be implemented by these social network companies. So just a few applications of our main result. So you can estimate the size of the graph, but you can also estimate the size of subgraphs. For example, you want to estimate how many users between the age 10 and 20 are there on Facebook. Conditioned on that you can get this information about every user, okay, in his profile, then you can just look at the subgraph and estimate how many users in this subgraph. You can get other things like the degree distribution, other health measures called the local clustering coefficients and more. And in general, we have something for any function f, you can get the median or other quantize of the values v1 to fvn, where v1 to vn are the nodes of the network. And just one final application is that you can use Fiat-Shamir to transform this protocol to be non-interactive. Then you get an argument, of course. This argument can be published once and for all and be verified by any user in the network using a few queries. So if you go back to this report, then they say they have 1.73 billion daily active users, and here in red, they can just add the proof for this fact. And again, you'll have some error, less than 1%, say. And the hope is that maybe this could be part of some next generation regulation that we have for privacy of data, specifically for social graphs. So we've introduced the notion of interactive proofs for social graphs. We provided an efficient protocol for monitoring the health of social graphs. Some open problem is eliminating this dependency on delta. I don't think it's necessary, as opposed to the dependency on tau. Of course, we can talk about other health measures, except the ones I mentioned, and maybe push this for standard in regulation. And of course, I don't have time to talk about the proof, but I'm happy to do that if you have questions offline. Thank you.
Thank you very much, Elon. So there is one question posted to Zulip for this talk by Cody. It says, do the mixing time tau and average degree delta need to be known in to the protocol?
Yeah, that's an excellent question. So you don't need to know exactly the mixing time and the average degree. You do need to have some upper bound on them.
I see. So is there any other questions for Elon? We are kind of over time, but if there is another question for this talk, we can take it before thanking everybody. So if you actually remembered any questions, you can post it to Zulip. So this was already done for one of the talks. Questions. Some of the questions for Lisa came after the talk was over. So hopefully you can check the answers also in the same Zulip thread. And if you had any other questions or comments, you can ask it, you can add it to that thread. We are a little bit over time, so we won't have a Q&A at the end of the session. But I wanted to thank every speaker, all the contributors, and all the attendees of this session. And we're gonna have the ISCR meeting in about 15 minutes. So with that in mind, hopefully